Hello everyone, welcome back to new video. In this video, we will be discussing about margin testing capabilities and the error injection capabilities of the Prodigy I3C exerciser and protocol analyzer. Starting from the margin testing capability, in the exerciser view, as you can see, we have a voltage function. This voltage parameter can be configured starting from 0.9 volt to 3.3 volt in steps of 30 millivolts. This actually gives the user the flexibility to test their target DUT at different operating voltages. Now we will switch to control scripting window. We will load on I3C initialization frame. So we are loading ENTDA command frame. So in this scripting window, the user can configure frequency, timing parameters such as TCAS, clock after start condition, TCO, clock to data delay, TSU-STO, setup time for stop condition, and also setup time for repeated start condition also. The frequency can be varied starting from 1 Hz to 12.5 MHz. This actually helps the user to test their pre-silicon target DUTs. We will send this particular command. Here actually it includes the reset DAA and ENTDA frame. We will start with initialization. So once this particular command is sent, in the plot view you can see the reset DAA and ENTDA frames are captured, and in the decoded result, the frame types for both reset DAA and ENTDA also decoded. Similarly, the user can vary this particular timing parameters and frequency. So now we will try with frequency of 5 MHz, and TCAS we will configure it as 4000 nanoseconds, and TCO we will configure as 30 nanoseconds, and TSU-STA we will configure 50 nanoseconds, and TSU-STO we will configure 100 nanoseconds. This particular timing parameters can be configured within the defined limits as per the MIPI I3C specification. So when we run this particular script again, the new frames which are captured in the decoded result and the plot view, this will be running at this particular defined timing parameters. To know more about how to do the timing analysis using the plot view, check out our other video. So by varying all these timing parameters and frequency, the user can test their target DUT, how it responds to any particular timing parameter which is configured. Now we will discuss on error injection capabilities of the Prodigy I3C exerciser and protocol analyzer. So Prodigy I3C exerciser actually supports error injection capabilities for the target DUT starting from TE0 to TE5 errors. We will start with the TE0 error, which is actually wrong broadcast address. So we are loading TE0 error script. As per the I3C specification, the broadcast address defined is 7E, but here we are configuring a wrong broadcast address, which is 3E. We will see how actually the target would respond for this particular broadcast address. So when the wrong broadcast address is sent, you can see the target is responding with NACK message, and also in the error column under the decoded result, it will get highlighted T0. Similarly, we will send some of the other errors also, such as command parity, data parity, which is TE1 and TE2 errors. So in the command parity, we are sending a broadcast command, which is a set MWL, set maximum write length, and we are injecting a parity error to the command. We will run this script. So when this particular script is sent, here you can see the expected T bit for the set MWL is 1, but as we are injecting the command parity error, the controller sends the T bit as 0, and also this will get updated in the decoded result showing TE1 error. Similarly, we can try for TE2 errors also, which is data parity. Again, the data parity for the first data packet will be varied, will be changed from the controller side. As you can see in the previous frame, the first data packet T bit was 0. Now we will send this particular script and we will check. So first time we will get a NACK message along with the HDR pattern, as it is a slave recovery or a target recovery method. So we will send it one more time. So now you can see the broadcast set MWL with a TE2 error. And as you can see in the plot view, the expected T bit for the data packet 1 is 0, but the controller is modifying the T bit to 1 and it is injecting a TE2 error, which is a data parity error. And also this is getting highlighted in the error column. Similarly, the user can inject error on the alternative data packets also, or else the user can inject error to all the data packets in the I3C frame. Now we will load one more script for a TE3 error. So this is injecting a data parity error to the ENTDA frame. So when we run this particular frame, here you can see there is a reset DA frame and there is a ENTDA frame which is coming with a TE3 error. Similarly, the user can inject TE3 error also. In the TE3 error, we are actually modifying the data parity of the dynamic address. As you can see, we already sent this particular frame along with the data parity error injection. So in the ENTDA frame, in the decoded result, the error column is getting updated with the TE3 error for the ENTDA frame, as we are modifying the data parity for the dynamic address. Similarly, the user can inject other types of errors also, such as T4, T5 errors for the target. And also we do have a support for HDR command errors such as HDR CRC error, HDR preamble bit error and HDR CRC token error. We will try with any of the HDR CRC command. So again we will load one HDR CRC error type. We will try with the HDR CRC error. Here you can see in the script we are including the error type as CRC. So this modifies the CRC packet of the HDR command. So when we send this particular script, in the error column you can see it is getting updated with the CRC error, and here the expected CRC is modified from the controller side. So now we are seeing the CRC packet as hex 393, but we will just remove this CRC packet error and we will send without any error injection. Now you can see the expected CRC packet is hex 38C. Similarly, we have support for other error injection also, such as HDR preamble bit error, HDR CRC token error. So these are all the errors the user can actually inject from the controller side. Talking about the target injection capabilities, we have a support for NACK error. So here you can see we will just send one NACK on 7E. So whenever there is a 7E broadcast address from the controller side, the target will NACK on this particular 7E address. So we will run this script, and from the controller side we will send one broadcast address. So for the broadcast address, we are loading ENTDA script only. So here you can see for the first frame, the target is giving NACK on the 7E message. This is how the user can inject error from the target side also, if the user is using Prodigy device as a target. So we will load one more error type, such as NACK on slave address. We will run the script, and whenever there is any particular private commands or directed commands with a target address, the target will NACK for the dynamic address. So here you can see for the first frame, the target will NACK. If it is the same dynamic address also, as we are injecting the error from the target side, you can see the target is giving NACK on the dynamic address. Using these all features such as modifying the voltage, modifying the timing parameters, modifying the frequency, using these all features, the user can do the margin testing capability of the target DUT, and using the error injection capabilities such as supported errors starting from T0 to T5 and CRC errors, HDR preamble error, HDR CRC token error. Using all these different types of error injection capabilities, the user have the flexibility to test their target with the different error injection conditions. Hope this video is informative. Thank you. We'll see you again in the next video.